Hello, everyone. Welcome to the first talk of this session. The speaker is Professor Zhengwei Liu from Tsinghua University and Binsa. He's an expert in quantum complexity and topological quantum field theory. And today, Professor Liu will discuss a new way to understand computational complexity. Please join me in welcoming Professor Liu.
Thank you for the introduction and welcome to my talk. And today I will talk about a new way to understand computational complexity. Well, it's mainly about the computational complexity for classical computer and quantum computer. And a main theme that probably everyone is interested in is whether quantum computer is really powerful than classical computer. And if it is, then how powerful it is, whether we have exponential speed up or super polynomial speed up or polynomial speed up. And we have learned some algorithm theoretically that has a lot of advantage. But in general, it's not very clear. Like in practice, so far people have tried many experiments to demonstrate the power of quantum computer. But every time one see a Nature paper about saying, okay, we achieved quantum advantage by demonstrating this algorithm experimentally, and then in the following couple of months, there will be many papers, like hundreds of papers saying, okay, we can do this by classical computer. So it's not that clear where is the benchmark. And today we will explore this kind of computational complexity and try to give a unified way to study all kinds of efficient classical simulation methods that showed up in this area. And we find a new way, new mathematical framework to unify them. So somehow we can see the limit, at least on our current knowledge, we can see the limit of those classical simulation methods. And we can see how far we can simulate quantum circuits or quantum algorithm by classical computer. And then there is a very small gap between the limit and the power of quantum computer. So somehow the useful algorithm is in that small gap. And then the question will be, how do we find such an algorithm in that small gap? So somehow we have a much better understanding now in this framework. Well, to understand this better, somehow this is an interdisciplinary subject with mathematics, physics, and computer science all together as a theoretical background. And if you really want to construct a quantum computer, then you need to learn even much more than that. It includes engineering and many other subjects, more complicated. But here we'll talk about the theoretical part, and we will mention some kind of experimental difficulty to implement the quantum algorithms. First, classical computer is really reaching the limit of Moore's law. That we know the classical computer, the computation power is doubled every year, but in recent year we can see the curve is decreasing. And the major problem is when we get to the limit of the size, then we really get into the quantum world. If we go below 2 nanometer, then the classical theory is not that effective. We have to consider quantum effect, and that causes major noise. But as another strategy, quantum computer has been proposed around 1980s to say, why not we just use quantum system to simulate quantum phenomena, and then it will be more efficient. And then furthermore, whether we can use quantum theory to build a real computer, quantum computer that can solve more universal problems. This is the idea proposed at that time and by both Manning and Feynman from different point of view. And one advantage is that in quantum system, the quantum state has a superposition. It's not just 0 and 1 like in classical computer. It can be the superposition. When we measure that, we can get 0 or 1 in probability. And this superposition can store the information in this so-called block sphere in much larger space. Yeah, but even though it's stored in large space, but you cannot expect you can read all the information in that large space. If you want to read all, you have to take exponentially many measurements to get all information. So this way involves additional statistical phenomena. Like what's the real information we can read out from the state in polynomial time? That's crucial. And that's also the major difficulty for many meaningful algorithms. They all have this kind of problem. So we can store information in state, but how can we read them out? So somehow quantum computer has 3 parts. You have input. So how do we input the information efficiently? And how do we do the quantum computation efficiently? So the middle part is nowadays mainly the main focus. Most people focus on the middle part. And then for the measurement, how do we read the information efficiently? That's not very clear. People have tried a lot. But if we want to combine all the three parts together and to make it really like exponential speeding up, that's a major difficulty. Somehow this is kind of the development of science. People are trying a lot and try what works, what doesn't work. And sometimes we take some ideal condition at the beginning and eventually it doesn't work. So we have to improve the methods. And that's kind of the storage of quantum information using the superposition. And it's not just single qubit. You can take even multiple qubits and also take the superposition. And that's the quantum entanglement phenomenon, like 0, 0 plus 1, 1. And that's also a very surprising phenomenon that's hard to believe at the beginning. In particular, Einstein doesn't believe that at all and proposed an inequality, the famous EPR inequality, to say, okay, if we really have such a entangled state, then here is an equality. We'll measure that the result should verify this equality if it's classical. If you can get the Bell state, the entangled state, then it won't verify this equality. So that's kind of a test. Somehow when he proposed that, he believed quantum entanglement doesn't exist. But eventually this is done experimentally, and the three guys win the Nobel Prize. So that's a very remarkable result, saying, okay, the world is really quantum, and we can have such quantum technology to build the computer. And for the state, that's kind of, we can have superposition, we can have entanglement. That shows the power of the storage also to build quantum memory. And for operations, we can also have more power for operation. Like in quantum system, we can have the time evolution of Hamiltonian, that's a unitary operator. And we can use such a unitary operator to evolve on the states. So this is a continuous map rather than just a discrete bit flip in classical computer. This also shows the power of this, the operation we can do physically. And in particular, if you take the superposition of states, you can do the operation on the basis simultaneously. So this is kind of parallel computation that's naturally appeared in quantum computing. So all those phenomena shows the power of quantum, the potential power of the quantum computations. Well, there are some useful gates, like for single qubit. Well, we have the, essentially we have the single qubit is a unitary gate, SU2. And we can decompose that as the rotations in the different directions. Like SU2 has double cover of SO3. You can rotate that in X direction, Z direction, or Y direction. And there's earlier formula saying that you can decompose the unitary as just a single phase transformation in different directions as multiplication of 3 of them. This last formula. So this is kind of a usual gate, and this gate has very high fidelity and current technologies. Like 99.99% we run this single qubit phase gate. And there are some useful gates, like single qubit gate, we can say poly word, poly XYZ. Like poly X is kind of quantum version of the bit flip. And we also have the phase flip, that's Z, and the multiplication is poly Y. And another useful, yeah. Oh. So here there are some elemental gates like poly XYZ, and the Hardeman gate changes the basis from X basis to Z basis, and a special phase gate is S gate, and another T gate with a more finer angle, like T square is S, S square is Z, and the 2 qubit gates control Z. And if you just run those gates, and those gates will generate a dense subsets of SU2. And say it's because you only take a discrete angle T. If you remove T, then this will generate a finite subgroup that's called Clifford group. And somehow we know this finite subgroup won't give quantum advantage because we can do classical computer computation to simulate those finite subgroup. But if we add a T gate, then yes, we can have a better generation set so that you can approximate arbitrary SU2 or even SU4 using the multiplication of those gates in polynomial time. So you can take polynomial number and with error rate is O to the with error rate epsilon, and the number of gate is O to the epsilon to the minus 3. So you can have a arbitrary small error rate epsilon, and then you can approximate this gate using those generation set. And the number of gate is polynomial. So essentially, accuracy, yes, like the distance from the the multiplication of the straightening gate and the SU4 gate. That's the small difference. This is finite. It doesn't matter which norm you are considering. You can just take the two norm. That's fine. Yeah. And also for this T gate, so for somehow for quantum computer, you can run error correction to implement those other Clifford gates in a more accurate way. And for T gate, it's very special. There is a tessellation method to make that more accurate. So there are some methods to improve the accuracy of those gates. But in general, if you can build those gates in high accuracy, then the more the better. Then you can essentially have a good SU2 and SU4 gate, like 2-qubit gates. And then you can use that to generate like 3-qubit gates and more. So essentially, those are the usually considered generating sets of gates. And that has good experimental implementation. And another gate that's not in this set is so-called Toffoli gate, control Z. And that gate is 3-qubit gate. And it's not 2-qubit gate. It can be generated by like 5-qubit gate, 2-qubit gates like this. But if you want to implement that directly, there is an experimental implementation, but not as that high accuracy, not like 99%, much lower. But based on new development of technology, maybe people can find better physics principle to implement those additional gates in a more efficient way. So this is kind of the mathematical structure behind that, and given a gate set, so you can take different choice of gate set. But the point is, which gate set is easier to implement experimentally, and this is a usual set. So what really makes most people interested in the subject is this famous algorithm, Shaw's algorithm. It factorizes big numbers. Okay, you can take a product of two paired numbers, P and Q, and get number n. And then if you want to factorize this number n, it's very hard, classically. So far, people don't know whether this is really like NP problem, but it's NP problem, but don't really know whether this can be solved in polynomial time. At least not just no such algorithm at this point. And most people believe this is hard. And this has been used to design cryptography, like RSA code. And it's widely used in current technologies in many different ways. So once the Shaw algorithm was posted, it was shocked to the community. So first, like factorization problem by quantum computer can be solved in polynomial time. And that means if we really have such a quantum computer, we lose the security protected by that, by RSA. So this is a big challenge. And after that, many people have tried to build new cryptography schemes to define the quantum algorithms using other mathematical structures. But still, this is the most popular one. And the algorithm is actually not that complicated. Just you take the n-qubit zeros and another copy of n-qubits, and then you run this multiplication. And the n-qubit, you can consider that as a binary number. You can write a natural number as a binary number. And the last line just means you take a number, just input number, say 1, and you multiply this input number by a constant, a. And you can take constant to be 2, for example. And then you just run this multiplication based on the previous input. And the previous input is just all zeros, and Harman map 0 to 0 plus 1. So that means the top half is just superposition of all possible bit streams. So essentially, if you combine the two together, then you just apply this number I to this a to the s power to the input. So the input will be I and a to the s power. And then you run this discrete Fourier transform into the n-qubits. And this is not a black box. This Fourier transform can be implemented by local 2-qubit gates. So it can be done. And then it's just a polynomial cost. And then you measure the result, you will get some number. And from this measurement result, you can, from this number, say x, then x over 2 to the n will be very close to the unknown value of this a. That means it's close to this k over r. R is the order of a. So from that, and then using this continued fraction theorem, you can read out the periodicity of a. And once you know periodicity of a, then you can use that to factorize this big number. in a very simple way. Just you read the measurement. Just this is small enough. And then from this x, you can read out this, figure out this r from the continued fraction. And once you have this order r, then you can try to factorize it in this way. And then if you choose a randomly, then it has a high probability, like close to 44% that r is an even number. And we'll factorize it in this way. The common denominator, the GCD between this number and n will be a non-trivial divisor of it. So then you factorize that. So essentially, this quantum algorithm tells us how to find this order of A by quantum algorithms. And this is a circuit, in general, it's called the phase estimation. And somehow Peter Shaw involved this phase estimation and using this classical continuous fraction to have to do factorization problem. Well, so theoretically, that gives us an algorithm that quantum computer can do in polynomial time and solve a problem that's hard for classical computer. And those kind of algorithms are called BQP. So the problem can be solved in polynomial time by quantum computer. And another class is called BPP. Those are problems can be solved by classical computer in polynomial time, in high probability. And somehow we believe this is bigger than that. Like Shaw's algorithm is here. This factorization problem, the factoring problem. So this is kind of the major argument that we believe in that quantum computer is the next generation technology. It can solve more problems than classical computer, more efficient. Well, but what's the challenge? That well, this is just purely theoretical. All the gates are performed perfectly. There's no noise. But in our real quantum system, we have to involve noise. Like for a single qubit case, the best rate we can get is like 99.99%. It's hard to compare with classical computer. But so far, we think it's already good enough. Like for 2 qubit case, it's even worse. For 3 qubit case, it's more worse. So people are trying to find good algorithms such that even in a noisy environment, it's still effective. So there are some remarkable algorithms. First is run by Google. That's the random quantum circuit. And essentially that using random quantum circuit, they produced a distribution from measurement. And somehow the distribution is hard to simulate by classical computer. And this is true if there's no noise. There's theoretical guarantee for that. But if there is noise, it's not clear. So they have to give some benchmark to show this is something hard to be compared, to be simulated by classical computer. And so far, the widely used benchmark is so-called Chaos entropy. But this benchmark itself also has problems. You can find some other distribution that can be easily simulated by classical computer, but with similar benchmark. But somehow we don't know what's kind of good mathematical criteria to say something is hard to simulate by classical computer. Because for quantum system, the problem is once you just read the distribution in polynomial time, you don't really know what you read out. If you want to know the full information, it has to be exponential. But in polynomial time, it's not hard. It's hard to say. But still, in that case, people have tried a lot of methods by classical computer to simulate this quantum, like random circuit. And they can eventually simulate the sampling process. So in that case, this doesn't have quantum advantage. And at that time, they use 53 qubits. And recently, they raised the number of qubits. So that is harder to simulate that by classical computer. But still, it's not very clear whether we can optimize the algorithm and then beat that again. It's not clear. So far, the two areas are kind of challenging each other all the time, frequently. And there are some other algorithms like the sampling method, and that's just a very natural method that you can produce using photonic techniques. It's just the physics nature. This kind of Boston sampling result, the measurement is just hard to be simulated by classical computer. But this is a very particular measurement. This is just particular sampling process. It's not useful for kind of more general quantum computing. We cannot use that to solve some meaningful like real world problem. So that's another thing. That's more like a quantum simulation rather than wild quantum algorithm. But so far, at least people showed from quantum computer we can produce something that's hard to be achieved by classical computer. And this is first called quantum supremacy. And later people take a more modified word called quantum advantage. This is quantum advantage. So this is kind of main theme. We want to reach quantum advantage first, and then we want to go further. We want to find something meaningful that can really help us to solve meaningful problem efficiently. And that's hard by classical computer. That's kind of final aim. And we want this kind of algorithm can be implemented experimentally. So to really understand what algorithm really have this kind of quantum advantage, somehow we need to know how far we can use the classical computer to simulate those quantum circuits. What's the limitation of classical simulation methods? And there have been several powerful classical simulation methods. The first one is given by the Clifford gates. Just those generating sets, but not involving the T gate. And the very interesting part is those Clifford gates, it can produce largely entangled states. So at the very beginning, people believe the entanglement, like the parallel computation, gave the advantage of quantum computing. But then we can show, okay, based on those Clifford gates, we can generate many interesting circuits, but like quantum arithmetic codes. But those gates, you can change the basis and read that in a different way, like the action on density matrix. Then this becomes symplectic transformation on the like 2n dimensional vector space and over the binary field. And then it doesn't have any advantage. You can do this by classical computer. Just take multiplication of symplectic transformation. So this shows entanglement is not enough to have quantum advantage. And another challenge is if we run those like topological quantum computing, like Tori code, then the gate that's with high fidelity, like fault tolerant gates, are those Clifford gates, not T gates. So if you just run the quantum like fault tolerant topological quantum computing on first level, it doesn't give you any quantum advantage. That's another challenging part. So then people started managing saying, okay, if this gate set doesn't work, then why not we add another gate inside this gate set? Then we get universality, like the T gate, and then we have a high accurate T gate by distillation, and then that will work. So that's a powerful scheme that people are trying to use currently. And another thing is this generating gate set called match gates. It's closely related to the Ising model. You can just take a 1 qubit transformation in the x direction and 2 qubit transformation in z direction. And then this is continuum site. But still, all their compositions will produce many interesting circuits, but they can be simulated classically. And because they can be computed using some technology of free Fermis. It doesn't have any quantum advantage. So those two are the famous sites of quantum circuit that admits efficient classical simulation. So both can be done in polynomial time, O to the n to the third power. And what makes it even more interesting is that if you combine the gate set, then it's universal. So it seems that it's very sensitive. If you just look at each one individually, it has classical simulation. But if you put the two together, you will not expect classical simulation because that's universal. That involves all kinds of interesting quantum circuits and involves many NP and NPC problem. And if you can say, okay, the combination is still have efficient classical simulation, then somehow P equals to NP. So somehow just that's not what we should expect. But still, general circuit is kind of mixing of the Clifford and match gate, hybrid Clifford match gate circuit. So we want to understand for those general circuits how far we can simulate them. So that's a central problem for the classical simulation of those quantum circuits. And there have been many other problems based on entanglement. And essentially saying that, for example, if I have the circuit like run in this way, like a very complicated circuit, and maybe with many qubits, but if the depth is small, then you can compute the value not in this direction, but mathematically in the other direction. And then this set, this width or depth becomes width is small. And then you can do the computation this way. And that can be done by classical computer. So essentially, if the depth is just logarithm, it won't have quantum advantage. And the useful quantum circuit should be something like linear depth or sublinear depth. So this gives idea. So you can compute those kind of like tensor network by a small piece. And even though it's very complicated, but if you just compute this piece, and then the output index is small. So even though the box indexes you have many, but the boundary index number is small. So you can just by compute this classically and just by brute force computation and put everything in the box to the boundary and just repeat this process. So this uses the small entanglement phenomenon. And they essentially just using this method and the previous computations, the group in Chinese Academy of Science, the Pan Zhang's group, they are able to simulate Google's random circuit by classical computer. And Professor Jingyi Cai, a leading expert in computer science, have a very nice framework called Holland framework. It essentially computes solving some counting number of field theory. And they show that just given certain tensors, local tensors, and then you look at all possible tensor network and try to show whether computing the value of tensor network is a P problem or NP problem. And then he classified, he gave a full classification, essentially saying if the tensor network can be solved in polynomial time, then the generation tensor will be either Clifford or match gate, just only two families. That also gave the unique conditions of those Clifford and match gate. So even though people started previously in a quite different way, but from the complexity theory point of view, they have their unique role. And they also show that if it's not like that, if you take other generation set, then computing those tensor networks is not just NP hard, but Sharpe hard, some kind of most difficult problems in this family. So either simple as P problem or Sharpe hard, nothing between. So then people are trying a lot to understand, okay, since we not just want to understand what circuit can be simulated classically, we want to understand the general circuit, like Shor's algorithm. It involves many other gates. We want to understand whether those general algorithm has classical simulation or not. So we need to consider those hybrid circuit of those general gate sets, which is universal. And this is a central problem, and people tried a lot, like Clifford plus T-gate, that's universal, and try to analyze if we don't have enough T-gate, like if you only have logarithm many T-gates, then you still have classical simulation. On the other hand, for Clifford gates, for match gates, you can add something additional to match gates so that it still have classical simulation. But for match gate, what's the meaning of additional? It's not that clear. The very interesting story is for match gate, it's related to some very famous problem called perfect matching problem for planar graphs. So the solving the solution of perfect matching of planar graph is the same as counting the value of certain planar match gate tensors. And that's famous work of Leslie Valiant, the Turing Prize winner, also ICBS Lifetime Award winner. And for that case, the very interesting part is for perfect matching of planar graph, this has polynomial algorithm, and they compute that using a Pfaffin matrix. That's also related to the free Ising model of the physics in the physics literature. But on the other hand, if you don't just take planar graph, you take general graph in the 3D space, then the perfect matching problem is NP hard. This kind of very sensitive. Planar is easy, not planar is hard. So this kind of the mystery in complexity theory, also mystery for our real world. Something in small set is polynomial, that's something we can do efficiently, we can understand better. But most things are not in that set. But somehow we want to challenge that part using more efficient methods. So then for matrix, essentially saying that if it's planar, it's easy to understand. If it's non-planar, then it's hard. But then for quantum circuit, it's actually not that easy to characterize what's the meaning of non-planar. But there has been some mathematical study on that problem. So those are the essential two families. And the long-standing open question is whether there is a unified classical simulation framework for the hybrid Clifford and match-gate circuits, and such that this method is efficient for both Clifford circuits and match-gate circuits, but not efficient for mixed. So when I first get in touch with this problem, this is a very natural one. In a sense, this is kind of question you ask, but this is not natural one to have a solution since the algorithm for classical, like for Clifford, is given by those symplectic transformation. For match cases, it's given by those kind of Fermi and Pfaffin methods. These two stuff has nothing to do with each other. We have no idea what's going on. There's no reason, mathematical reason behind that to unify them together. And if we can unify them together, then the following question is, then what's the major computational difficulty? We have to have some additional concepts beyond the two, and that's still difficult to compute. Otherwise, P equals to NP. So we want to understand what's going on. And then it takes a long time to understand the structures. What's the meaning of Clifford? What's the meaning of match-gate? Whether we can find the unified framework, mathematical framework, to understand both concepts in a natural way and combine them together. So that's kind of the aim. Now we are going to introduce such a mathematical framework that give us a solution and give a broader view to understand the computational complexity. And the very exciting part is this broader view comes from with new ideas in topology, and in particular low dimensional topology, 2+1 dimensional. And that's quite relevant to the famous 2+1 topological quantum field theory, which have been studied quite a lot. And many fields medalists have major contributions in that area. So we do have a lot of mathematics and physics behind that we have learned. And now we can use that to study computational complexity. Like when Kitaev proposed Tori code, essentially he used TQFT to build quantum error correcting code. Now you can use TQFT to study quantum computing complexity. So what is this language? We call it QAnon language. And QAnon really means the QU is kind of the prefix for quantum, and the ON is for the particle. And we put them together, and we propose this together with Ask Jeffy. It's called the QAnon language. And recently, actually, we found that there are some other things called QAnon algebra. Even though we are talking a different subject, not relevant, but the name comes from the same reason. Also, some kind of quantum particle called QAnon. So this is kind of a good name. And why we call this a language? Because like tensor network, when we draw this graph, it gives us language to communicate, to compute. And QAnon language is also a picture language that to communicate, to compute. And also, actually, when Wheaton first proposed TQFT in his original paper, he mentioned that TQFT should be considered as a powerful computational tool. And here, indeed, we implemented that for quantum computing. So what's the relation between the tensor network language and the TQFT? It's very natural. Just in tensor network, you just have those tensor product of vector space. Okay, single qubit space is two-dimensional. If you have vector in three single qubit space, you have these three leg answers. And this is a tensor called copy tensor. You have input 0, then the output will be 0 and 0. If I input 1, your output is 1 and 1. So it's 0, 0, 0, plus 1, 1, 1. That's the tensor. And then in the Qt language, we extend that to a 3 manifold in the TQFT. And the bulk of the manifold is just the neighborhood of this single tensor. It's kind of this fat graph of this one skeleton. And what's more is on the boundary surface, on 2D boundary surface, we have additional defect lines. And those defect lines are given by the black box in the previous tensor network language. Now we transform that into white box, something we can understand well, we can compute. And this gives more insights and more efficient computational tools in this for these defect lines. So the translation from the tensor network to the Qt language is quite straightforward. And our first step is just trying to understand those generating tensors for quantum circuits and translate those generating tensors to our language using those defects. And then find complete computational rules and then do efficient classical computation. So what we have on those defect lines? So at the beginning, we only have those defect lines. Those are like 9 intersecting circles. And the value of each circle contributes to the so-called quantum dimension, that's square root of 2. And then we can take a linear sum of those like 9 intersecting circles, like those crossing. It's just a certain linear sum of this diagram and that diagram. And in particular, if you choose special parameter, you will have a braid verifying the red mass moves. And those braid has been applied by Wang Jones to construct the Jones polynomial. And here we are using those solutions to construct such a braid, like the one in the middle. So essentially, by those linear combination, we have a general crossing with arbitrary parameter theta, and we can also have some special parameter, and to get a braid or pair of charge. And those special parameters, like braid or pair of charge, correspond to the Clifford gates we mentioned before, and the general parameter corresponds to match gates, the arbitrary phase transformation. And since we are involving the 3 manifold, and it's coming from the neighborhood of this one skeleton, so it's essentially a solid torus. And then in solid torus, we can see those holes. So it's a heterogeneous solid torus, and we can see those holes. So somehow, after we translate the tensor network to TQFT language, we will see those fundamental elementary ingredients. We can see holes, we can see those braids and charge for Cliffords, and we can see those crossing with parameters for match gates. And this gives also a universal generating set in this TQFT to simulate tensor network and quantum circuits. And then if we just have the first 2 structures, just have holes and braids and charges, then essentially we produce Clifford. And that's necessary and sufficient. Somehow, if we take all such kind of 3 manifolds with appropriate boundary condition and such decoration, it is just Clifford. So this is a very nice mathematical characterization. On the other hand, if we take match gates, and then the corresponding 3 manifold will be just a ball. It has no holes. So if we just take the other 2 structures, the crossing with parameters on sphere, then we will get match gates. So this gives a mathematical framework to unify the 2 concepts in a very natural way. The first 2 Clifford, second 2 match gates, altogether that's universal. And first 2 are easy to simulate classically, second 2 are also easy to simulate classically. So after we observe that, then we want to understand in this language whether we can understand those classical simulation algorithms for Clifford and match gate, and whether we can unify them together. But after we observe that, it also takes like about 10 years to figure out a solution. And now we'll present this solution. And actually, when we proposed that in the paper, Bill Monty asked this explicit question for the Clifford part. Just in Qt language, whether we can do efficient classical simulation for Clifford circuits in polynomial time. And there is a very natural motivation why we ask that, because previous Clifford circuits are given by the symplectic transformation. But here we represent all data using those braid charge and holes. Those are all just bit information, not qubit information, just bit. We store the information is just classical information. We just need to find computational rules to do this computation in polynomial time. And this is something we can do, and it's become part of this main theory. So in our theorem, first we present those generating tensors for match gates, just as like 1 qubit tensor of these 3 tensors in those graphs. You can see the parameter of the match gates is given by those parameter of crossings here. And for match gates, there is a very interesting phenomenon that's no matter how you draw the tensor. So first, for a single qubit, it always have 4 boundary points to encode the 2-dimensional subspace. And for the match gate tensor, you always have those lines on the boundary side, like parallel lines, go along the boundary of the surface. And then when you compose those tensors, you will see an interesting phenomenon. Just for each hole, those boundary lines will be a closed string surrounding the hole. And then we have a so-called string genus relation. When a hole is surrounded by a string, we can remove them. So that will kill all the holes. So that means for match gate tensors, or planar match gate tensors, we can remove all those holes. If it's not planar, then okay, we don't have enough rules to remove all the holes. That's the major difference between planar and non-planar phenomenon here. And it's encoded in a natural way. So for planar tensors, we can remove all the holes. And for Clifford tensor, we can also write down all those generating tensors, like single qubit case and 2 qubit case. And essentially, it just involves all those diagrams, which may have charge and braid, but not the parameter. It can also have holes when you take compositions. And then in recent 2 papers, in the first one, we say, okay, how do we characterize the simulation of those methods? Now we can find some new states that can have a classical simulation, but not known before. And in the second paper, we find those simulations and we design the algorithm, the classical simulation algorithms. And this is based on this QL language we read before, and our recent work on TQFT, called autofold TQFT. That's how we extend the theory from this like solid torus to general 3 manifold. And in TQFT, it gives us a lot of new insights to do the computation efficiently. So we found new computational tools from the TQFT. And the TQFT is trying to work with Shuangming, Yilong Wang, Jinsong Wu at BIMSA. And this second paper is joint with 3 students, Zixuan Feng, Fan Lu, and Ningfeng Wang here. And this paper is joint with the MIT group, and my friend at Harvard will meet, actually, both of them will meet at Harvard when we started this project, when we propose this Q1 paper. So it really takes several years. And actually, in this paper, we not just, in this program, we not just solve this problem for solving this open question, but we solve another problem, say, we really write a joint paper between Chinese group and the US group. That's even more challenging. They have to, like the last have to write a lot of reports to say we need to have such kind of collaboration. So we hope this kind of problem will be more frequently solved in near future. But we don't know whether that's really the case. That's just much harder. So in the first paper, we propose this linear graph showing, okay, we want to see which kind of state have classical simulation. And previously, we know the metric product state and Clifford and match gate, they have classical simulation. Now we can find something additional to the match gate, something more than that. And this becomes a very popular subject in recent years. People are trying to use some new numerical method to find more states that has classical simulation, like DMRG methods. Well, the second one is our main algorithm that we have this size that admits classical simulation. And you can see this remarkable family, Clifford and match gates, the smallest circle. Now we find a new family that involves both. And actually, in addition, we find a new feature to characterize this computational difficulty, the exponential computational difficulty. That's called the magic holes. And if the number of magic holes is logarithm, then it still has classical simulation. But if it has more like linear number, then we don't know. So that will involve in the more general hard family. So So essentially, just given any tensor network, we first translate that to the Q1 language. We get this 3 manifold, and then we compute those values. The value of tensor network becomes the partition function of the 3 manifold with defects on the boundary. So we just find those tools to compute the partition function in TQFT. And then we can write down the value of tensor network as some kind of partition function in TQFT as a state sum. And usually the TQFT has a very big state sum, it's exponential. But we have new ways to reduce the computational complexity on the level of TQFT. And essentially the exponential complexity K is given by the number of magic holes. This is no notion we found. And the computation formula is just even better, just the previous you have a constant factor to certain power, and this number is just some combinatorial data. It's an integer, half integer. And this part is just the product of some Pfaffin matrix, which has polynomial time algorithm to compute that. It's square root of the determinant. And then just take the sum. So we have this formula. And this is the algebraic formula, but essentially we really do this formula in a topological way rather than an algebraic way. But this is a clear formula to show how do we involve Clifford and Matchgate together. And actually, for Clifford, essentially you don't have a Pfaffin part. And this number is 0. So you only have one term. And this gives you the result for Clifford. And for Matchgate, you only also have one term. You don't have magic hole. And then you compute the Pfaffin. So this is kind of Clifford and Matchgate. And in general, we mix them together. And this part is kind of the entanglement between Clifford and Matchgate. So what is this magic hole? So we go back to this picture. We have those 3 elementary ingredient holes, and the braids, and the general crossings. And the first 2 are easy to compute. And the second 2 are also easy to compute. And if you consider the first 2 to be easy to compute, like if you run Clifford algorithm, then this is hard. This parameter is hard to compute. If you run the Matchgate algorithm, then the hole is hard. In our new algorithm, we say, okay, neither the hole nor the parameter are hard to compute. But when they entangled, when they compose together, that's hard to compute. For example, if you have a hole surrounded by this crossing, that's hard to compute. And this is the new phenomenon, but very natural. So why we have this feature? Because in TQFT, if you have such a graph without a boundary, you may have a hole in the middle, but without boundary, then everything, no matter how complicated the graph is surrounding the hole, it will always reduce to this graph, because given this boundary condition in TQFT, this vector space is 2-dimensional. So this is also a spin, but with a hole inside, so we call it topological spin. And this also shows a very crucial physics phenomenon, that the spin in condensed matter might be an emergent phenomenon of those defects given by the hole. So it will be very interesting to study those kind of lattice models with those emergent spin. The condensed matter physics might be also emergent. And nowadays, many people try to say field theory, like myself, I would prefer to say like field theory and many other geometry phenomena emerging from the condensed matter. But then we ask further question. Like a couple of days before, I also talked with Liang Kong. He has similar idea, saying whether spin in condensed matter is also an emergent phenomenon. And this is kind of model saying yes, in this model, it's also emergent. And this is kind of key feature. This spin is the major difficulty. That's kind of the elementary ingredient that's hard to compute. And that's the topological spin. And for quantum computer, or for quantum complexity theory, so this is kind of a long-range entanglement. You have a hole, like a global topological phenomenon, like in Tauri code. You have those kind of hole to encode the logical information. And here, you have this hole surrounded by this diagram around that. So that essentially has a long-range topological entanglement. And this parameter, if it's the braid, then this is long-range entanglement, but it's Clifford. And if it's not braid, it's called long-range magic. Nowadays, people have been studying a lot about long-range magic. Somehow we believe this is the part we can find quantum advantage. And this theory gives this kind of mathematical framework to explain, yes, for long-range magic, that's essentially necessary, the necessary part to have quantum advantage. So after we have that, then we can combine the two methods together. Let me go back. We can combine two methods together. So how do we compute the Clifford part? Just that's essentially saying, like, how do we design an algorithm to compute both? And the interesting part is, if we have a hole in the diagram, if everything surrounding the hole is just Clifford, then we can remove the hole. And this algorithm is similar to the original Clifford algorithm. If just look at hole and look at all the graphs surrounding that, if it's just this kind of braided diagram, then we can remove the hole. And if we have no holes, if we just have crossings, those crossings satisfy the Young-Baxter equation or randomized move. So you essentially can, if it's a local disk involved in those crossings, you can essentially using the Young-Baxter relation to remove them and eliminate the crossings. So you won't see those crossings locally. So eventually, the only remaining part is just those global crossings surrounding the hole. After the algorithm, that's the remaining part. So we finally didn't really use the Fafi method to compute that. We used the kind of those kind of randomized moves of nodes, but for these general crossings. So now, after we have this algorithm, then we can use this to simulate many interesting circuits to see whether this has classical simulation or not. Like Shor's algorithm and many other algorithms. Essentially, we have some theoretical guarantee saying if the algorithm has no noise, like Shor's algorithm, then it can solve some hard problem. But in the real situation, the algorithm will have noise. And once we have noise, then it's not that clear whether the quantum advantage is still true. And then we have another method to simulate not just circuit, but those noisy circuits called poly path, like path integral of those, well, just like we have polyword decomposition of circuits at a noisy position and then take the path integral of that. And then for this integration, the interesting part is when the polyword has less number, we can compute that one by one by our classical simulation method. Every single term we can compute that. If you have more polyword, then that means you have more noise. And that will be a term that has exponential decay in the average case. And so if we combine the two, then essentially we can show for most quantum circuits, or if you take quantum circuit randomly, most of them have classical simulation. So only a very small class will have quantum advantage. And then the question is whether we really have such circuit even in a small class. But more importantly is whether we can have such a circuit that's meaningful, that can really help us to solve problems in the real world. It's not very clear. So essentially, this is something we can do experimentally. And this is, the first one is something theoretically good. This is something we can do classically. So this will give a new benchmark. We can do numerical simulation to see whether the real one is close to the better theoretical one or to our classical simulation. And then this distance will tell us whether this algorithm is closer to quantum advantage or closer to classical simulation. So that's a better benchmark to characterize the efficiency of quantum algorithms. And we use such kind of benchmark to test some algorithms. Once we see this path integral method, actually, we can show, like for variational quantum algorithm, which is closely related to those so-called quantum machine learning, as inspired by the current development of AI and many other things. And they always have those variational algorithm or variational quantum circuit, and they train the parameters. But here we essentially show just for those variational part, most of them have no quantum advantage. And at that time, IBM proposed a paper saying, they published a paper at Nature saying, okay, they run their 127 qubit quantum system, and they are able to solve some meaningful problem. And that's hard to simulate classically. And it has two parts. One is the algorithm with noise, and the second part is the mitigation. The idea is actually very interesting. Just it's hard to minimize the error rate, but you can enlarge the error rate. And then when you enlarge the error rate, you can interpolate the error rate, and you find the one that has like zero error. That's kind of mitigation process. And then we write two papers. The first one we use path integral to show, okay, for the result, for the experimental result with noise, we can simulate that classically. with high accuracy and shorter time. So then that won't have quantum advantage. And then we can run their mitigation method to get the same mitigation results. In the second paper, we say, okay, even for mitigation, we can also find a good mitigation method by classical computer, and that has better mitigation effect using those kind of Q language idea. So essentially, this doesn't have a quantum advantage, but still, this is kind of the current status. We are always trying to understand what really has advantage, what doesn't, and that needs the more stronger development or kind of more better development of the experimental site to have better or somehow more like to have a higher accuracy of those physics. And this is the concrete graph. Just our simulation and their simulation are just on the same line. And we cannot even distinguish the two lines from the graph. Okay, now let's come to this Shaw's algorithm. As we explained, Shaw's algorithm essentially tells us how we find this order. That's how the quantum algorithm tells us. We find it from the measurements, and we get this order. That's the main rule of Shaw's algorithm. And then we compute this probability of Shaw's algorithm, and without noise, Shaw showed that if you want to run this method, he gave a lower bound to show that you can find such a good measurement to get the order with a constant lower bound, like 2 over pi squared. So that's the main point, saying this algorithm works. So you can have a constant lower bound for probability. You can always find such that if it doesn't find, then you just repeat your experiment multiple times, then you find that. And from that one, you find this order, and then you factorize the large number. Now, let's see what I explained. Now, with the noise, what happened? The probability with noise will become a formula. When lambda equals 1, the formula is the same as Shaw's probability. But with noise, this probability will decompose in two terms. One has lower weight, one has higher weight. And because of noise, the higher weight part has an exponential decay. Depends on the strength of noise. So essentially, if the weight is large enough, this is close to 0. So that means the higher weight part will be destroyed by the noise. For low weight part, we can still keep that. That's the effective part of Shaw's algorithm in a noisy system. So we can still do factorizations. But for this part, we can find a classical algorithm in polynomial time to do the same task. So Shaw's algorithm, in that sense, it's not clear whether that really have quantum advantage. But again, this classical algorithm has a very, very high polynomial degree. So it's not in practice impractical. Like usually, if it's n to the 3, we can do it like classical computer. If it's n to the 1,000, it doesn't make sense. So for complexity theory, for this problem, it makes a lot of sense. Whether we can really find an algorithm with noise, that's BQP, not BPP. We know Shaw's algorithm in perfect sense, without noise, is something like that. But with noise, not clear. And essentially, this method not just breaks Shaw's algorithm, it breaks this phase estimation method. So the other famous algorithm is called HHL algorithm that solves linear equations. That also uses phase estimation. So essentially, for all quantum algorithms so far, most of them either use this phase estimation. No, it's not clear whether it has this kind of advantage. Second class is variational. And then using the Path integral method, it's not clear whether they have advantage. So we don't really know whether there is a meaningful quantum algorithm that really have exponential speed up in a noisy environment. So we hope to see some more advanced theoretical work to understand this major point and to have a better understanding of algorithms. So whether we can find some meaningful algorithm that's really in this class, in noisy environment. But maybe that's just not true. And also another thing is that we can run quantum error correction to minimize this effect of the error. And then the classical simulation is possible, but it will require very, very high degree. That means we can use quantum computer to do the task much, much faster than classical computer, at least polynomial or even super polynomial speed up. And we already have many, many applications in fundamental science and in real world applications. And also this classical simulation method can help us to several other things, like design quantum arithmetic codes, quantum algorithms, and reduce the cost of experiments using more powerful classical simulation by classical computer. Thank you.
Thank you, Professor Liu, for interesting talks. So let's see if anybody from the audience has any questions.
For match gate, it's a planar one, and all the output are on the boundary of the disk. A function means the output may be inside the disk. Yeah, this has classical simulation because even though it's not planar, we compose them, but when we measure that, you fill all this, then it becomes planar. Essentially, it's still planar status.
Any other questions? So I have the sense this should be sort of a goodness parameter, some function at the side of the problem.
Yes.
New behavior or transition behavior.
Yes. So here the noise parameter will affect the polynomial degree in classical simulation. If noise is small, like if the noise is like this, like this is just 100% noise, then the classical simulation will require this kind of degree, like n to the 100. It's really large. So when you have like 6 digits, then this will be like 1 million. So even though it has classical simulation, but it's just not meaningful classical simulation. So if we pay attention to complexity theory, then this does fall into classical one. But in practice, that shows the quantum computation is very powerful. And in particular, if we run the quantum error correction, then it only takes polynomial cost to minimize this noise. But here, it's polynomial, but this degree increase much, much faster than error correction. So that's kind of, we need to compare this kind of polynomial degree rather than polynomial or exponential.